Hi, everybody. Uh, oh, okay, great. So this is episode number 7, I think. We are January 29. In a couple of days, actually, it's my birthday, so it's actually kind of
Oh,
cool.
mine too.
Which day?
31.
Oh,
Tomorrow my
I
time.
am February 2nd, so crazy,
Okay.
incredible.
Hmm.
We are very close. So anyway, yeah, so this is the physics of Bitcoin with Giovanni and Stephen. And for the people that are familiar with our show, you know what it's about. Basically, we are trying to go a little bit deeper into different Bitcoin-related topics from a scientific, general scientific angle, but in particular using our experience from physics. And some people will wonder, why do you use physics to understand Bitcoin? Because physics works with everything. It works with human phenomena. It works with biology. It's supposed to be a different way of understanding the world. And maybe one day we should have an episode of why physics is relevant to Bitcoin. And, we could do that. But we are trying to make this argument little by little by introducing different topics. In fact, Stephen today will have very relevant analogies and techniques. It's a question of using methods, analogies, way of thinking, relationship with other phenomena that are somehow similar, not identical, but similar to what we observe in financial systems. Anyway, so you had a slide to discuss the agenda today, right?
I do.
And let me activate your slides and you put them up. Okay. All right. We should be able to see the slides.
Okay, good. I think it is indeed number 7, Physics of Bitcoin. Pleasure to be here again with you, Giovanni, and with the audience. And I talked last time about the two-phase nature of Bitcoin, power law and bubble. And I want to expand on that. I've done some additional tests that really nail down, the strength of this case, that it's two-phased. First, I want to say a few things about liquidity, because we've been in a little bit of a liquidity doldrum, and we're sort of waiting for governments in particular to turn on some liquidity taps. And US and China are the most important there. It seems like private liquidity has been picking up, according to Steno research. So that's good. But I want to just show a couple of slides about that. And then we'll get into the whole issue of two phases. And we'll start with some quantile regression that shows you really from the beginning that there are two phases, but we're going to drill down with hidden Markov models, looking at the histograms, breaking those down into different time frames, looking at something that's called KDE, which is basically a probability density. It's another form, sort of like a histogram, but more continuous. And then we'll look at survivability as you're in these different phases. Two main ones, but a transition phase, so 3 phases in total. And then we'll talk about the issues that you have with quantile regression. It's got some downsides, so we'll talk about that. And then the reason, of course, is that you have these bubbles, and so quantile regression starts to break down when you're in the bubble regime or bubble phase. And so we're looking. Did a very quick cut yesterday. Actually, it was my wife's birthday last night. So during the party on my phone, I'm doing some quick work to look at taking out the second Gaussian bubble and redo the regression and see what happens there, so that we can, kind of deal with this issue that quantile regression has and deal with the distortion that the second Gaussian introduces. So let's get into it. First, on the capital inflow. capital inflow itself also has to follow a power law. In other words, if we're going to sustain, and we have sustained Bitcoin's power law of nearly the 6th power over these 16 years, and if we're going to continue to sustain that, then capital inflow has to pick up. And it has to actually pick up according to a power law. It has to keep growing in a power law. And it's simply the first order derivative with time of the 5.8 power law. And therefore, it's a 4.8 power law. Now, it gets a little messy because you have something called the market multiple. So if I invest $1 into Bitcoin, that has an effect on price that's greater than $1. And that's called the market multiple. But on average, it runs at about 2.5. Cena of 21st Capital just did a study of this. He found 2.4. It bounces around a lot, but over long periods of time, it's, probably less than 3. So if you assume a constant over long periods of time, and then you just do that derivative, then you're going to need capital inflow growing as the 4.8 power of the age of Bitcoin. And currently,
let me ask all those questions too. And sorry if I interrupt you.
No, please.
So why the derivative? Right? I understand, but I'm trying to ask.
Yes, of course.
From the audience point of view,
Right.
Why the derivative? And first of all, what the derivative means, and why we are assuming the capital flow is a derivative.
Yeah, great question. So, Bitcoin has a certain price and a certain associated market cap, multiplied by 20 million basically today, right? And that's $2 trillion, right? And we project 40% growth per annum based on the power law, a little bit higher, but about 40%. So that means that 800 billion increase in the value is the power law trend. So next year, putting aside bubbles, it would be worth 2.8 trillion market cap, right? So that's really the derivative. It's the change per unit time, which in this case is annual, right? And since it's a power law, you want the change per unit time. So it's the delta in price or the delta in market cap per unit time. So dP over dt. And since t is going 5.8, you're taking a derivative, of a power law, an algebraic relation, and you lower the power by 1. And so that's how you get.
It's an analogy. It could be like you're looking at the flow from a faucet, right? And that is something that happens over time. And so the derivative is describing this change over time. But if you want to calculate how much money comes in or much water comes in the sink, you will have to calculate the flow of a faucet. And this is what you're doing.
Great. Yeah, that's great analogy. We're filling up this basin and we've got the flow come in, but we don't actually need 800 billion because of this market multiple, because price moves by more than the dollars coming in. So it turns out that right now, if you divide by that market multiple, you need something like 320 billion per year in order to sustain the power law.
Yeah.
And that turns out to be about 20 times what the miner's revenue is. So you need 20 times the miner's revenue. So that already shows that what the miner's doing is kind of irrelevant, right? Because it's only a 5% effect, whether they hold on to their coins or sell them. So that's what we need. Now, so that means that this graph that's plotted, which is a log linear graph, it has Bitcoin age in years, is saying how much of investment capital do you need, assuming a constant market multiple, and then just using that derivative relationship. If the market multiple were dropping over time, you'd have to take the derivative of that term as well, and it would get more complex. But let's just assume this for simplicity. And so if we're at 16 years now, you can read off from there that it's of order 300 billion that you need. And as you get to 20 years, it gets close to 1 trillion. And as you go out to 30 years, when the age is almost double from now, then you need something like 6 trillion coming in. About 6 trillion coming in every year to sustain the power law. So the conclusion that I draw away from that is that maintaining the power law needs the big capital to come in. And where is that big capital? It's with corporations, pension funds, and governments, right?
Yeah.
It's not.
Now it's basically beyond what single investors can do, unless you had an incredible inflow of investors. But even that is a power law. So,
Well,
yeah.
what these corporations, pension funds, and governments are just networks, right? They're networks of individuals.
Yeah, exactly.
And so what you're doing is you're opening up some more channels. Think about the ETFs. You're opening up more channels for the liquidity to flow in, for the capital to flow in. But they are doing it in a broadcast fashion, in mass, by making it easier for the individual. BlackRock doesn't own most of that Bitcoin, right? It's owned by the people that buy the ETF shares.
Yeah, fantastic point. Because basically it's just an organized way of bringing in a lot of people at once, right? So BlackRock behaves as a whale, but it's made by many small little fishes, So yes.
Yeah. Okay. So the next one is Michael Howell's observation that, and I know you've done some work on this as well, Gio, that Bitcoin is a power law of global liquidity. And Howell, who, by the way, this is a very good book, in this Capital Wars book by Michael Howell. He has his global liquidity index that considers not only the government money, what's in the central banks and the treasuries, but it looks at all the banking system, the shadow banks, the large capital allocators, and looks at their effects on liquidity as well. And this is a log plot. Now, these are not log 10. This is natural log, just so you get a sense of the scale. Yeah. But it's a span from when Bitcoin went from $200 to $100,000. And he finds with the dashed line, which is the simpler model, that it's a 9.72 power law of his global liquidity index, nearly the 10th power.
Marley, and on the Y scale, these are a real number. I mean, is these logs or the values of the liquidity?
This is his, right. This is his value. Value of the log of global liquidity.
But it's not millions, 10 million, right? So this 6, 7, 8 is not a logarithmic scale, right?
Yeah, it is. It is. That's the price. That's the price.
Oh, the price. Okay, so you're showing the price, and then you have a
Bitcoin's on the y-axis, and that's
I see. I understand what you're plotting now. Okay, and then on the x-axis we have this index. But the problem is the index didn't change much, right?
That's correct.
That is a little bit of a problem, because when you have small changes, almost everything looks like a straight line, right. But it's okay. But it could be. When I did it, I really didn't see a power law, also because it took a long history, from the beginning. What this covers, it seems that does it cover like recent data, right? It doesn't cover the entire history.
This is recent data. I mean, basically, you've got a factor of about a little over 0.5 is a natural log. So it's the square root of E, right?
Right.
So it's only about 1.6 ratio on the GLI.
Right.
So that's the limitation you're calling. Of course, it's a much bigger spread on Bitcoin price itself.
Okay. Fine.
Yeah. So it's, there's something there, whether it's, he says it's an R squared of 0.9. It certainly makes sense at some level that we know that markets are influenced by liquidity availability, the stock market and bond markets as well.
Yeah.
And we know that Bitcoin correlates to the stock market and NASDAQ. And we know that it's much more responsive. So it makes sense that there could be a high power law, but we'd like to see a broader x-axis, right?
And the exponent is 9.7?
Correct.
Mm-hmm. Pretty big.
It's very big.
Yeah.
The only thing that's bigger is hash rate.
If this was true, then it's almost like Bitcoin is a liquidity multiplier, right? You put a little bit of liquidity and it responds very strongly to it.
Yes, Bitcoin is the most responsive to liquidity, is what he's arguing.
Right.
And he claims that it's strongly Granger causal in a statistical sense, and that the liquidity, and I don't have the graph here, but he's done the tests for lag and lead, and he says that liquidity leads Bitcoin by about 11 to 13 weeks, so about 1 calendar quarter.
Uh-huh. Okay, I need to do that test myself. Yeah.
Yes.
That's interesting.
Yeah, you might want to do the Granger causal test for the lead lag. Yeah. Now, this is from his latest newsletter summary. This part is public. I don't subscribe to his newsletter, but this part is public. As to what he says our current environment is, that central bank liquidity is recovered, collateral values have ticked higher, which is a positive component. The US dollar has lost some momentum, and that is liquidity positive, but more is needed. The risk asset markets, gold and crypto, he does mean Bitcoin really, have reacted to changes with some delay, and they've recently lost momentum because of the liquidity slowdown that started in October. It will be supportive, he thinks, towards the spring, and he believes that liquidity will expand further this year before peaking around Q4. That's interesting timing, because that's when you think the bubble peaks, right?
Right. In fact, I have what I did, and one time I took his model, because it's not, I cannot reproduce it. I don't know what it does. It's a little bit complicated. Maybe one day we can try, but what I cheated a little bit, because he had like a sine wave, and I saw where the sine, he say what the periodicity was.
Right.
I think he says 65 months or something
like
that. And then I look at where the peak is, where the trough is, and I cheated and I reproduced the same curve. And because it's a sine wave, and it was peaking this cycle, in this first time it happens in Q4. So that is interesting.
Okay. Now we have this possibility of freezing government spending. That would be a drag. So that's that's not going to be helpful on liquidity.
No.
Okay. Now into the quantile regression, and I showed this last week, but just to refresh, this has got 7 levels. I don't go crazy on my levels. I don't go to 0.99 and 0.999 because you have 0.1% of your data. I mean, we'll get into those issues in a moment, but this has got 7 levels, 0.05 up to 0.95. And, so already from this, you get hints of the 2 phases, because you see that the lower 3 levels are all bunched up. And then the red line, which is the median line, quantile 0.5, is getting close as well. And then the 3 levels above are well spread out. And this is a power law in gold of 5.54. And in dollars, you get, with the same technique, you get 5.82. Okay, now let's look at...
Can I make a comment, if you don't mind, if you could go to the previous slide? So there is all this debate, right? I'm going to write an article. I'm actually sending you a preview so you can give me some feedback on the article. Basically, this entire idea, because I want to find a positive angle, basically explaining to people what is modeling and what is good modeling and what makes sense. And now I think the most difficult thing for most people is to make sense of these graphs, right? Because if you are trained and you have worked with these things, it's relatively easy to understand them. Sometimes you have to spend some time with the graph, even for professionals like us, but most people have no clue. So one of the things that people don't realize, that is a quantile regression, that for some reason is becoming popular, because some people are pushing it as the ultimate way of understanding Bitcoin, but I think it's nonsense. Pushing it in that way, it's a useful tool, but it's not for sure the ultimate way of understanding Bitcoin. What is not explained often, that is basically another way of doing the power law. It's just that instead of using the classical method, that is what is called least square regression, that has its own problem and its own assumptions, because that is part of what happens. There are always assumptions. When you make a model, there are assumptions, and these assumptions can be, justified, not justified, can have limitations, but the assumptions are there. There are always assumptions. Even in the quantile model is trying to have less assumptions than, for example, the least square approach, but the assumptions are still there, and we can discuss what these assumptions are. But if you are making a model, like in this case, where you are asking the code by indirectly, by writing, by asking ChatGPT to do that, and then ChatGPT will write the code for you, or by actually coding it yourself, you are basically asking to draw a straight line, because the input that we give to the code is logs. It's log of the price and logs
Right.
of days from the Genesis block. Once you do that, and you're asking to find linear regressions, because this is what the quantile method does, even if it is a different way of doing linear regression than the least square method, you're asking basically, in other words, to find power laws, because a straight line in a log-log graph is a power law, period. And the result is funny, because notice you get a bunch of power laws. In this graph is less evident, but basically you see how these different power laws have different slopes. So which power law is the true power law? The true power law, please stand up.
Right.
Which one it is? It turns out that very likely, and there are many reasons to think so, it's the bottom line. The bottom line is where the real power law is. The other power laws that you get are the best that the quantile method can do, because you're telling to try to fit a straight line where there are no straight line. And so it gives you a straight line. If you have a hammer, everything looks like a nail. That is what the quantile method does. It's trying to draw all this straight line, and it gives a little bit of nonsensical answer to say that here there are a bunch of straight lines. There are not a bunch of straight lines. It's just the best that this method can do. And so it needs interpretation, and and maybe you can go and explain what the interpretations are, how to make sense of these.
Right.
But we have to be careful about these things, because people can get confused, right? So it's a big deal for us to talk about
the whole point of what I want to present.
Exactly. So please go ahead. I want you to. Sorry,
so,
I hopefully I didn't take too much of your time.
Let people just notice that as we go from age 2 years to age 16 years, which is what's covered here, actually 1.6 to 16, that the width between the bottom line and the top line contracts by a factor of 2. So these lines are on a path to converge, and then some of them cross each other, right? And that's what Giovanni and I would call unphysical.
Right. Not just that, actually, if you use I can show you a graph later where if you use a partial data, up to a certain point, there is a point where the crossing already happened. That is even more problematic. And they dig more. And actually, this is what several sites were saying, that is one of the main criticisms that not just us, but other people raised towards the quantile model, that is a typical, not typical, but it happens often, where these quantile levels cross each other, and that has a real serious interpretation problem, because
I'm going to set that up. I'm going to set that up for you. So
yeah.
Okay. Happy birthday. Oh, God. Okay, so this is a histogram of the residuals, and it's binned with 0.05 bins. So it's all the residuals for the full period.
And the residuals are basically the difference, right? So you're taking your model and then you subtract the real price from it, right? This is what is meant for.
I've taken out the 5.5 power law, which is the one that corresponds to the median, the 0.5 quantile. And these are the residuals that remain. So since that's the median, some are negative and some are positive. And we see this long positive tail. We know that Bitcoin is right skewed, right? Which is a great thing. We like that. It's convex. But we also see that, the most frequent residual is slightly negative. And that's our core power law territory.
Yeah.
And then we see it goes down to this dip at 0.2, and we have, only a few residuals around 0.2, and then it goes back up to a secondary peak, and that's when you're in bubble territory.
Yeah.
And so it's immediately apparent to the eye that this is two-phase.
Yeah.
Certainly to the practice eye.
Yeah. So the and
But
that,
I want,
I'm sorry if I interrupt you here.
yeah,
Sorry
go
for all
ahead.
the interruption. That is our physicists talk, because physicists are a strange mix. We know the mathematics of a mathematician. We can be as rigorous as you want, and we know the practicality of an engineer. But we are in the middle, where we're trying to bring real physical science to the data. It's a skill that you develop as a physicist, a very important one. And many times we use our eyes. How many times I told you the power law is so evident that you can use your eyes? It seems a childish thing. Oh, I'm using my eyes. Yes, you're using your eyes, because many times when there is a real signal in the data, your eyes will tell you what is going on. And then you do the more sophisticated analysis to show that it's real, that you're not making it up, etc. But you always start with your eyes, to get an intuition of how the data looks like. Is it true, Stephen?
Intuition is a skill all physicists need to have.
Yes.
Yeah. Okay. So I want to draw that out and really build the case for that two bubbles that I started to make last week. So I divided the data into two sections: the first 8 years roughly, and the second 8 years. And what we see is, again, two bubbles for both of these distributions. They look a little bit different. The first 8 years, the residuals are much broader than the second two, right? And this is as we know, the volatility has come down, and the skew maximum has come down. The peaks, are not as high. So, we see a maximum of 1.25 in the blue case, the younger case, and we see a maximum of 1.0 or just under for the more recent ones. And we see the same thing on the left-hand side. And it's also a little noisier in the first 8 years. So it's actually gotten better. The residual range is tighter. The bimodality has been sustained. But the peak locations are in about the same value. It's like minus 0.1 and plus 0.4 in the log 10, where the centroid of the two peaks is. Now, you can also do something called a probability density curve. It's called KDE, kernel density. It's just kind of a continuous histogram, and that's the little inset on the right, on the left, above the thing labeled histogram. And then the next thing you want to do is try to fit two components. And so I've used a Gaussian mixed model to fit two components, a bimodal distribution with two Gaussians. And it works quite well. And it has about 56% of the weight is in component 1, and 44% of the weight in component 2, which would be the orange dash line, and then over to the red line.
I use another method, roughly counting, and I got counting how many data points below and above the power law, and I got similar numbers. Very good.
Yes. Now, remember on the last slide, I said that the centroid was minus 0.1 and plus 0.4. So that is a difference of 0.5 in the log 10, and that's a factor of 3. So when you're in bubble territory, on average, in that second component, that second peak is at 3 times the price of the core power law. Okay, so this is how I had actually kind of done it first, was by eyeballing it. And I just kind of used intuition, looking at the residuals, and said, well, we've clearly got something two-phase. And so I'm going to divide it into the upper and the lower and transition. And so I used a 40-20-40 split. And so the red is the upper volatile bubble zone, the high points. The green is the base power law zone. And you see that the volatility is much higher, of course, in the above. It's about 3 times higher. I think it's about 2.8. in actuality. And then you see the yellow zone in the middle, which are these transition zones, and they're very sharp, transitions. It doesn't spend a lot of time in those. But also sometimes you get fake outs, right? So between age 6 and 8 years, you had a couple of false breakouts that didn't persist, and they were out of cycle, if you will, right? They were not matching the roughly 4-year cycle.
Yeah, and there were reasons, like for example, recently I discovered. So we know which one, the one in this current cycle probably is associated with the ETF infusion and FOMO.
Yes.
But there was an event in 2019 that was associated with the Plus token, and so recently actually it came to the news because China is trying to sell these coins. They seize the coins, but basically it was like a big scam that created some liquidity problems with Bitcoin and influenced the price. And this is why the price went away from where it was supposed to be. So it's very interesting that there are local events and can create this situation, but they need to be really big, like the ETF, and then the price still goes back to where it was supposed to be.
Right.
That makes our thesis even stronger.
Now, this is Bitcoin gold. If you have plot the same chart in Bitcoin dollars, do the same analysis, then we're actually just into the red zone now. But it has not been confirmed by Bitcoin measured in gold ounces. We're still in the yellow zone for there. Cool. And we would have to add, right now we're like 38 ounces. And previously it was about 40 ounces fair value in this chart. And that would mean you'd have to get near 50 ounces to get a breakout. Okay, now, that was based on my intuition and a kind of arbitrary division. Now I've done something that's not arbitrary. The only thing that's arbitrary here is I say, look for 3 phases. So this is called hidden Markov models. And it basically looks for probability of transitioning from one state to another. So it finds where the phases are. Amazing. And what you see is what it found is almost precisely what I had found. Yeah. With my 40-20-40 split.
Yeah. Intuition is a powerful thing.
There's one slight difference. Around age 11 to 12, I found a green zone, and the hidden Markov analysis did not say it had entered the green zone. Now you can see the level was kind of getting to the green zone.
Yeah.
But the hidden Markov was saying, well, maybe I'm still in the yellow. Have I really transitioned yet? And it never enforced a transition. But cool. Generally, it looks quite similar. So it determines the probabilities of transitioning between states. It estimates the most likely current state and also predicts the probability of entering a bubble or a correction. And so it builds something called a transition matrix. And without showing you the matrix itself, I've shown you here the interpretation of the matrix to add a little more understanding to it. Basically, there's bubble persistence. There's a 98% chance that Bitcoin will stay in a bubble. Now, these are weekly data points, so that sort of corresponds to a 1-year roughly duration for a bubble. There's a very low probability of reverting to mean, about 2%. Overvaluation tends to persist. Doesn't mean you're going up necessarily. You might be going down and still be overvalued, right? Mm-hmm. Half the time you're going up, half the time you're going down.
Right.
There's slow transitions. There's no direct high to low transition, so that you never go from the red zone directly to the green zone. You never go from the green zone to the red zone. God candles are not a thing. There are no God candles here.
Yeah.
The mid regime is the transition zone. It's likely to stay there. 94% of the time it stays in the zone. And when transitioning, it's slightly more likely to fall back to the low than to surge into the high. And those are these fake outs that we saw. The momentum from mid to high is weak, but so you have to build momentum over time, and then finally you make your transition. It's like you bump up that $100,000 level, 3-4 times, and then finally you crossed it.
Right.
And hopefully it holds. Where are we now? 104, I think. Not sure.
And then can you read the last point? Did you cover the last point? So you say
Which
okay, when the transition is like I see, and this is so the low regime, right? The green regime is more like a mean returning regime, right? If it
that's the power law core, and it's
yeah.
reverts. It always reverts to that.
Yeah. If you do the Hurst coefficient, it
Mm-hmm.
tells you more or less the same story because it's one of my
Okay.
indicators that I'm using. I created a Hurst coefficient just tailored for Bitcoin, and you get similar results because, more or less we are discussing the same thing. Yeah.
Okay. Then this is another way of looking at it, survival analysis. Can you stay in the zone? How long do you stay in the zone? So the low zone, we talk about half-life for decay processes in physics. If you have a free neutron, it's going to decay on average in 10 minutes. It has a 10-minute half-life. And, the exponential decrease is 15 minutes. So we've got a 7-week half-life for the low zone. And the chance of making it for a full year is 10%. So that's interesting. You're not going to stay there longer than a year. You probably break out, at least to the mid zone, right?
Mm-hmm.
The mid zone has a half-life of about 4 weeks. And the chance of making it 1 calendar quarter is about a 10% chance.
Mm.
So you just look at the line and how the line steps down, right? And
I
see
love
where
this. It's
where it
so
steps to
beautiful.
0.5 and then down to 0.25 and down to 0.1.
Yeah.
And then the high zone, it's 24 weeks, about half a year, but on average, but it can persist to over 90 weeks. So the bubbles have the most persistence.
Cool.
But if you're in the bubble and if you're at 24 weeks, you've got a 50-50 that you're going to be heading, down again, right?
Right.
It sort of says, don't press your luck beyond 40 weeks or something, right?
Uh-huh.
It's this nice plateau. Very interesting, this plateau that is running from a little over 20 weeks to over 60 weeks. That's quite interesting. So I think we need some more detail on that.
Now, one refinement could be that we separate going up from going down, but I don't know how to do that.
Yeah, that's the next step. That's what I'm trying to struggle with next.
One of the things I want to see if you verify this result that when we go down, the exponential decay, it's very similar from bubble to bubble. That is really different in terms of the rate of decay. It's always something close to 0.2% per day or something like that. And has been very consistent for every single bubble. If you plot it, it looks like parallel lines, right, in a log linear chart. I wonder what that is due. I would like you to study that and do it. Let's figure out, because it seems too regular to be just by chance.
Right. A little over 1% per week.
Yeah.
Yeah.
And if you draw like a peak to bottom, like a straight line, right, like the equivalent exponential, you get parallel lines, and it's evident when you go up they are not, because they are shallower and shallower lines when you go up, but when you go down they are all the same. It is interesting. Like, what is going on there?
Yes. Yeah, we need a survival analysis that will work in both rise and fall directions. Okay, I just put some words into your mouth. Quantile regression is problematic, and I want to add something else. Ordinary least squares is problematic.
Sure.
So, we have these tools, and you have to know how to use them and when to use them and how to interpret what's been created with the tools. So what I've done is now I'm thinking about how do we remove that bubble so that we're only looking at the first Gaussian, that that bimodal peak, right? Remove that whole second peak, which is 44% of the data, and redo the analysis. So I've done that. I only had time so far to do it with monthly data, but very good result, actually.
Yeah, genius.
And so it's ordinary least squares and quantile regressions are both shown on this plot. The OLS is this solid black line, and the same levels of quantile are shown with the dashed line. And you see that the OLS regression is right on top of the 0.5 quantile. And in fact, they both give the same power law index. One is 5.58, so it moved up by 0.04. The other is 5.57, hardly different.
Yeah.
The error is about 0.036 on the power law index slope. And the R squared is phenomenal, it's 0.996. And the F test is 24,000, with only 100 data points. That's great. The Quantile regression, the range of slopes is tightened up considerably. It's 5.5 to 5.7, and you can see the lines are much more parallel to one another, right?
Yeah. And actually, one of the things you can do is to see if these holds if you use only partial data. Like, for example, when it's kind of like the bottom, right? You're showing the bottom or anything close to the bottom is still following a power law if you exclude the bubbles, right? If you eliminate the bubbles and you keep it's actually almost scary if you plotted. One other thing you can do, like, it's not really clear on your graph because you where the data points are, right? If you took out it's scary when you plot actually the data points that are left over when you eliminate the bubble, and you can see this straight line in a log graph. It is by your eye. It's a I want almost to say a bad word, F crazy straight line, and it's shocking because imagine you are leaving the straight line, you go to these crazy tops, you can't go down. It takes about 2 years, and 2 years later you go back to the straight line. Something is going on, and anybody that denies this doesn't understand anything about science, life in general. It's absurd. It's absurd.
It's a dynamic range of 1 million times.
And you go there, and 2 years later you come back. To exact. It's almost like the bubble didn't exist. You can draw a dot from the last time you left, from when you left the bubble, and it connects. It's ridiculous. It's I never saw, even in when I was working in neuroscience, I never saw data like that.
No, you don't get data like this in astrophysics.
In astrophysics, even it's just ridiculous. People don't realize when we say this is a power law, we make a big deal. It's not just a line. It's something really strange and fundamental about how Bitcoin behaves. There is no doubt. Anybody that knows anything about their field knows that. They can see that. It's reproducible data. You have just to look at it in the right way. Yeah.
Good. Okay. So I think this is my summary slide.
For curiosity, did you try to do the same using only the other the other distribution of the data and see what you get? Because that would be also interesting.
Okay, I guess it would be, but what we really need to do is model them differently, right?
Yeah, true.
Because they're not power laws; they're exponential.
They are not power laws.
And falls.
Yes, exactly. Yes.
Yeah.
Now, do you know what?
Yeah.
And this is what I tried to tell you the last time. You recover the power law if you correct the deviations by volatility. If you correct the deviations by volatility, and then you try to fit these, and you basically recover the price by correcting for these.
Oh, sure.
Then you get the power law again. So it's almost like there are two parallel power laws, one below and one above. And that is also interesting and give us a clue of why the peaks go down, because it has all that. In a sense, you say already that it's linked to the power law, because the power law implies diminishing returns. It's part of the equation, right? Like if you can rewrite it and show that the returns, that this price today or the price yesterday are diminishing if you have a power law. And this is why the entire thing will go down.
You're filling up a basin. All the turbulence is on the surface of the water. The basin volume is continually growing, larger and larger and larger. All the turbulence and the waves remain on the surface.
Exactly.
You're lifting up that whole thing as you fill up
Yep.
the basin with the power law. Okay, that's my transition into fluid. Bitcoin laminar turbulent system. So we have laminar flow that's stable and ordered, follows the power law trend. The low quantiles see that. The transition zone is somewhat unstable. It has some nonlinear growth. Its volatility increasing, but it hasn't gone to full turbulence. So you have this heartbeat, and it has this cycle of 4-year heartbeat, and you've got laminar flow inside your aorta, and it transitions with the heartbeats into turbulent flow. So this process is happening in your body every second. And as you go into the turbulent flow, chaotic and high energy, it enters bubble phases, and price grows exponentially above and then collapses exponentially back down to the power law. Thank you.
Thank you. This was fantastic. Yeah, it's beautiful. Yeah. So and when you say the least square as problems, can you explain for our audience what you mean with that?
Sure.
And in fact, maybe you can say in general, kind of what you already say, but let's say it in a different way. There is no one single way of doing these things, right? We are trying to come from different angles, and certain approaches are better than others, but they all have some limitations, right? Some more, some less, but they all have limitations. So what you were
so imagine we had no bubbles. Imagine that the volatility was constant all the time. Then we would have a power law with volatility, and you would do a quantile regression, and it would be fine. And the power laws would be parallel to each other.
Yes.
And the median would be on top of the ordinary least squares mean, right?
Correct.
So that's kind of it.
So how that will look like, just to explain. In fact, when I write my article, we use that.
It would look like a series of straight lines.
Yeah, and the data will look like a fuzzy power law.
And the data would be spread out between those bands.
It will be like a straight line, right, in a log graph with fuzziness, because data is never, like the theory says, when we say there is a straight line in the data, it's a simplification, right? There is noise. There is always noise. That is another way the physicists think about data. We are looking for a signal, and then we know there is always noise. There is noise that comes from our instruments. There is noise, in the process itself, because things are somehow random. But there is some kind of dynamic, some kind of a process. Like if I throw a projectile, the projectile will follow, the laws of physics. It's all laws of physics, but let's say more simple laws of physics, that is Newtonian physics. But then there is turbulence, then there is wind, and so the trajectory is not going to be perfectly like the textbook says. It's going to have some noise. And the question, in physics is always, how do we separate the signal from the noise? And all these techniques are nothing else than this. We are trying to extract the essence, that is the signal, from the noise. And given the type of noise, then you apply different tools. And the quantile, unfortunately, the quantile regression doesn't work very well because they have this very strange deviation. It's not meant to handle things like that. It's meant to handle things that maybe, like, for example, the Gaussian method, like in the example that Stephen gave, will work very well if the deviations were Gaussian. That means, this typical bell curve. Then it will be the perfect tool and probably optimal. There'll be no other, you agree with that? There'll be no other tool that will do better than the least square. Now, you can still use a quantile to tell you, okay, how big the deviations are, etc. it will be added information. But you could do with least square and then add parallel lines, right, to the least square with or maybe a fraction of a standard deviation and so on, and it will be still a pretty good representation of the data. The quantile method doesn't overcome this all of a sudden. So if we have this, it will be a little bit better if you add non-symmetric deviations, right? But up to a point. If you start to have very weird things like these bubbles that are periodic, that are decaying over time, it's too much for even the quantile model to complete represent. It's already amazing that it's doing a good job with the data below the median. And like Stephen showed, that is doing an amazing job with that. It represents, and so that actually a good thing, for example, Plan C, that is a fan of SINA, that is a good, you pointed out, okay, here is this very robust method to describe a behavior below the power law. Above, no, we need to find another way of representing that, right? And maybe we can work on it, etc. This ideal of bimodal is probably the best approach. We lost you, Stephen. We cannot hear you. No, do the same thing. Maybe you need a new microphone. We lost you. No.
Hello?
Okay.
Hello?
Yeah, we got it.
For some reason, it turned down my input volume. Okay. Look, if with the thought experiment I just said, you wouldn't have any skew, right? You'd have a log normal distribution, a Gaussian in the logs.
Yeah.
And so then it almost wouldn't matter, right?
Right.
Which method you use.
Yes.
So the quantile is fine at catching the core behavior, because that's true power law behavior for those low quantiles. But that's not what we have. We have really important and profound bubbles from time to time. And so they need a different approach. They need power law plus or power law plus minus.
And that was kind of what I was. So I'm going to show you this graph that I showed the last time, right? And we don't have a lot of time because let's keep it within 1 hour. But given that I have a few minutes and we are talking about this topic that is, kind of interesting. It's not even about, oh, your model is worse than ours or whatever. There are all different way of talking about the power law. So it's fine. It's just that we need to understand what they do. And so, for example, in this slide here, let me select the right slide. Okay, so, and I had an argument with Plan C. Let me explain the nature of this argument. I see this is so normal for me that I don't even need to, I didn't think about, I need to explain this because, and Stephen can confirm, right? We are used to do these things called toy models. So basically, we make something that is a much simplified version of what we think the real phenomena is. We know from the start it doesn't represent the complexity of what we are studying, but we do it on purpose because we want first to test our method of analysis with simpler things that we have control. So, for example, if I make a model like this, I know it's an artificial model. It's not, Plan C was calling it straw manning. It's not straw manning anything. It's actually saying if a quantile method is as he tries to portray it, a universal way of describing data, that is kind of works for basically anything, then it should also work for my little toy model. And what my toy model does, basically, I did a power law. I created it. So I introduce a power law in the data. So I know there is a power law. I know the slope. I did it like a Bitcoin 5.8, something like that. And then I added some sine waves. This is slightly different from what we see because really we see a bottom power law and then bumps. It's not really symmetric around the power law. It's actually even more complicated to model that. But I try to do something close enough. So power law plus oscillations, periodic oscillation. I made it faster to see several of them. I made it like, I think 1 year or something like that, 1 year oscillations. And then I added a decay, okay? And you can see clearly when you feed this, because this is the quantile method. I use the algorithm for the quantile method. Plan C always shows the right graph and not the right. And it's not clear from looking at the right graph that these lines, these curves are straight line. They are straight line in a log-log graph. So by definition, a straight line in a log-log graph, it's a power law. It's simple to show that it's true, mathematically, with just simple algebra. If you have a straight line in a log-log graph, and that, it doesn't have, but it has to be a special straight line. Basically, it doesn't have to have higher terms, right? But will not make it a straight line, but it doesn't even have a constant, because the idea is that it starts from when the phenomena starts. So in this case, if you use as your time days from the genesis block, basically that is what it is. You are drawing, it's basically some kind of equation that says y equal mx in the log-log space plus a constant. The constant is not, it's basically the y-intercept, right? Of the so when I mean not constant, I mean you start from zero, basically, right? You don't have an arbitrary time after zero. So your process starts from zero. And so that you can show easily that straight line in a log-log graph, it's a power law. It's simple algebra. Maybe one day we show to everybody how to derive that. It takes like a couple of minutes. So, and you see that is exactly what we get on the left. We get a bunch of straight line because the algo is a little confused. It doesn't know how to describe these things. You are telling, use an hammer to go through these screws. Well, it will, have you ever tried to put a screw in the wall using a hammer? You're not going to do a good job because it's not the right tool, right? You have to use a screwdriver. It's kind of like that, right? Is this a decent analogy of what is happening here? Right? You're saying, fit me a bunch of power law because this is what you're asking to the algo, and you get what you ask. It's a bunch of power law to try to describe this complicated phenomena where you have, something that is not just a power law. Yes, there is a power law.
Let me simplify it.
Yeah.
Take the very top line here. What color is that? Some kind of cyan
light
color.
Blue. Yes,
a light blue color. So is that a 99 quantile? I don't know. Let's just say it's a 99 quantile.
99 quantile. Yeah.
So it's looking for 1% of the data. So it kind of goes through the first curve, peak, and the second one, third one, fourth one. So, okay, I've got 1%. Then it just kind of keeps flying into outer space. It doesn't need any more data. It's got its 1%, right?
Exactly.
So it just stays on its straight line until it gets to the terminus.
So, it gets the first a few peaks. It kind of looks like a straight line because anything looks like a straight line. That is the point. You can fit a straight line through almost anything. In fact, is what the problem with S2F. It does kind of the same thing. You have these clusters. I can fit a straight line. It kind of looks like a straight line, so I can fit. It's similar. A similar idea. I know that it's not that bad. S2F is even worse, but this is what is happening here. It's taking the upper values. You get your 1% quantile, right? Your 99% quantile because it's the top of the data. And then it says, well, okay, I'm fitting a straight line like you asked me. And that is kind of your projection for the future. Does it represent some kind of upper limit? Yes, but it's so, disconnected with what is going on that it's almost useless. I could have drawn a straight line through the data anyway by myself, and say this is the upper limit. It doesn't mean anything.
It's wrong by 2 orders of magnitude.
Yeah, it doesn't mean absolutely anything.
Yeah,
it's you could say
not useful.
It's not useful. It's not useful because remember, there is this saying: all models are wrong, some are useful. I think it's a wrong statement. It should always be said, to be useful, to be right, a model needs to be useful. It should be post it in another way, because that is the goal of making models. We make model because they are useful representation of the data. If I make a model that doesn't tell me something interesting, important, useful, then it's not a model. It's not a good model. It's not something that I can use for a particular purpose. In this case, we are trying to understand future price prediction, both for the bottom, for the top. We want to look at the range of action of Bitcoin. And you can see another thing you can notice, right? You see how the different peaks go through different quantiles. So if you wanted to associate meaning to a quantile, say, okay, the top quantile, first of all, you have to tell me how you select that quantile. What is your criteria to say that is 99 versus a 90 or versus 85? But let's say I take a face value what you say. You say 99% percentile is my tops, right? It represents the top. You can see that that is not true, because the oscillations, as they go down, they cover many different quantiles. So each quantile doesn't have a particular meaning. It's not associated with anything significant of this price action. They go through different sections of the sine waves, as the sine wave changes. So, and you can say how much you want that this is an artificial model, but if a quantile was supposed to deal with any type of data in a very unbiased way, it should be able to deal with this model. Do you agree, Stephen?
To sharpen the point, basically what you're showing, Giovanni, here is that the Quantile model is providing hopium that you're going to reach what it claims is a 95% or a 99%, and you will never reach there.
Right.
So
yeah. That is the other side. So you could go backwards and say, this is what I'm waiting for C and plan C. Please give me a meaningful explanation of what these quantiles represent. Because if you say, well, forget about tops and bottoms, it's telling us that, it's very difficult to reach this peak. It's only, above this quantile, it's only 5% of the data, so it's very difficult to reach there. But I still have a chance, right? Like in Dumb and Dumber movie, right? Are you telling me that there is a chance? Are you telling me this that I have still actually, even with the 99, there is 1% chance? No, there is no chance, because you can see from the model that is not what these peaks are doing. They are not going there, and they will never go there. In fact, it's worse and worse as time passes by. There is even less probability that they go there.
So the question is, it's wrong, but how wrong is it for the next cycle? So I think you've got another chart.
Yeah. So, for example, you mean the one where I use real data?
Yes.
Okay. So
maybe it's not wrong enough to matter, right? How wrong is it?
It does matter.
Yeah.
Also, because we have to think about, you can see from my graph that things get worse and worse with subsequent cycles.
Right.
But even if you, for example, you play this game and say, let me use partial data, right? So, for example, here I use data up to the second bubble. And by the way, same thing happens when I use data with the third bubble. It's kind of the same thing. But you see, the red ones is my prediction, right? It's future data that I don't know yet. Often you can pretend this game when you do this calculation. You can say, let's say that I just knew up to the black data, and then I fit my model to only this data. Will I be able to predict the future? In this case, we know the future because we know what happened, but basically we pretend like if it was the future. So you can see it doesn't do a good job. Maybe it kind of did an okay job with the third bubble, but by the time you go to the fourth bubble, it doesn't, right? And that difference seems small, but actually because we are in a log graph, it's huge. Probably a factor of 10 almost, right? It's a big U. It's not a factor of yeah.
That is a factor of, looks like factor of 5 in linear terms.
At least 5, right?
Yeah.
So and you can see though how amazing the bottom is, because even with this little data, we got the bottom almost perfectly. So we don't have this problem, but is exactly what Stephen explained tonight with the bottom, because there is a real power law there. You see, there is not a power law at the top, but there is a power law at the bottom, and it finds that. It really finds that. In fact, I went all the way where I have another graph. I don't have it here, but I posted it in the last few days, where you can go and use 4 years of data. Only the first 4 years of data give you already the bottom. So imagine this: you were year 4, that is what, 2013. So yeah, you were in 2013, and you could predict where the bottom was, like the $16,000 that we got, a few years ago. And it's incredible. It's just unbelievable. And you can see with your eyes, it's a straight line. It looks like a straight line. The bottom looks like a straight line. And the method is very good with this. It is not very good with the tops. There is no back and forth arguments, discussions. We can have it. We can have Sina coming here and Plan C and discuss with us. But I don't know what they will see that say that will make sense, that will debunk what we are saying. There is nothing to debunk. It's just a question of understanding the data, what the data tell us, what these methods are about. It's not a question of, using some kind of book definition or texting, quoting the textbook. The textbook doesn't know about these particular weird real life examples. That is the entire idea of going from a textbook to real life situations. That is what research is all about. You leave a textbook behind and you go on in unknown territory. The people that come up with the Quantile method, I'm not sure they could foresee dealing with situation like this. It's not the proper tool. It's not the right tool to deal with data that has complex dynamics like that. It would be okay. An ideal situation for the Quantile model will be, you have a power law. When you have data that is not necessarily Gaussian, around, there is noise that is not necessarily Gaussian, maybe has even a long tail. And in that case, the Quantile model will be superior to the least square regression. But not in a situation like this, where the data is much more complex than that. Are we along the same line?
We're aligned.
Yeah. Anyway, guys, I think these are makes it for our show. We maybe can take a few questions. We don't have many this time, so we can go pretty quickly through them.
I saw one question on the number of states in the.
Exactly. So this, I think, is more pertinent.
I just asked it to find 3 states and to find, what data belonged to each of 3 states, because I had already noticed that it looked like we had 3 states, basically, 2 important ones and a transition one. So I asked it to do that. If somebody wants to go look for 4 states, that would be interesting too.
It's you don't have to answer it, because many times we don't remember by heart these things, but you have a high level understanding how the Eden Markov model works. How does it? Because maybe that is the nature of
it's just looking for the probability of a transition. So from one week to the next, it's saying, all right, what's the chance that I will transition to a different state?
And how do you think he finds the definition of what a state is by doing this?
Well, I asked it. How does it find a definition? I mean, it goes through a sorting process.
Okay.
And it makes some assumptions initially, and it iterates.
Right. It's kind of one of these optimal, kind of like the quantile regression, that is an algorithm. It's not really a simple equation. It's a sorting algorithm. The Eden Markov chain works in a similar way. It kind of optimizes a process where it creates, the states. It tries to identify, okay, if I add to divide this process, that is basically the transition to go from one state to another, then I kind of identify these three things. And it's incredible that he was able to, without not much more assumption than just showing the, because he didn't tell it, oh, there is a power law in the middle. You just show the the deviations, right?
I just showed the residuals, yeah.
The residuals. So you show the residuals, and then they are derived by assuming some kind of power law process. In this case, using the quantile regression, the median, right? You use the median of the quantile regression.
I use the median of the quantile regression to define the residuals.
It is a power law, not like Sana says, not a power law. It is a power law. It's just another way of finding the power law that kind of agrees with the least square regression, very close. And then you separate, right, the data in three states, and the algorithm does this in trying to optimizing a process. And it's crazy because you can see very well, again, with your eyes, that corresponds to particular phases of a Bitcoin behavior. So it's a really cool method. Anyway, guys, we are over the 1 hour. Hopefully we made an interesting show. I think we did a good job. One more time. And so, unless you have something else as concluding remarks.
No, pleasure to be here again. Happy forthcoming birthday.
Yes, same thing with you. Okay, guys. Thank you so much. And